不错不错。
Hello, hello, testing. Wi-Fi liên hồng. Okay. Hello. Okay, let's start first. Later I have an announcement to make. Yeah, let's start first. Okay, we'll continue with compactness. Sorry, last lecture there's no recording. I'm not sure. I forgot to press, I think. But I think not much content other than discussing the midterm. Yeah. Okay. So, okay, I started recorded already. Okay, so the first theorem we'll see today is if you are a compact subset of a topological space, if and only if it is a compact topological space itself. Okay, so how to view a compact subset as a subspace? Okay, you need to view it as the subspace topology. Okay, so what's the difference between these two statements? Seems similar. First, you have compact subset. The other is compact space with subspace topology. What's the difference between these two? Sorry? Yeah, sure. This statement is about biconditional statement, but what's the difference between these two statements here? Huh? What does it mean by compact subset? What does it mean by compact space with subspace topology? What's the difference? How do we cover a subset? Do you still remember how we cover the subset? The set is just required to be contained in a union of some open cover here. Okay, and then every subcover is finite. How about a compact topological space here? View it as a subspace topology. So how does the open set in subspace topology look like? Huh? How does a open set in the subspace topology look like? Zhenye. Yeah. What's the open? How is it open inside a subspace topology? Huh? The keyword is intersection. Sorry? Finite intersection, no. You need to take your open set in your topological space, intersect with your subspace. Okay, these are the open set. Okay, inside A. Okay, as a subspace topology here. Okay, so here you need to see A as union, okay, of all the intersection of A between. Then you need to check whether you have finite subcovering from all these. So not that these two are, there's a subtlety here. One, I just require you to be a subset. The other one is equal. Okay, because if you view A as a compact topological space, this is already the whole space. Okay, but previously, the previous statement it just say that it's a subset. Okay, does it make sense? So the picture in your mind, how should you imagine this? Let's say these are A. This one is A. Okay, so for subset, right, you should bear in mind that there's an X outside here. Okay, and then these OI are just something like this. Okay, but in X A, this OI we just take OI intersect with A. Okay or not? Can you see a difference? Can you see difference? Okay, the second picture here is just this OI intersect with A. So lie entirely inside it. Can see? Okay. So the statement here is if you can find a finite subcover, okay, for every open covering, in this case of compact case, it is true for the if you view A as a subspace topology. Is it clear why is it from this picture? Can you see why? If you start from one picture, you have open covering, okay, and then there's a finite subcover that covered it. After you take intersection, this finite subcover should cover your A as well. Okay, similarly, if you start from A, okay, because these OI are actually coming from some open set in X. Okay, actually they are coming from some open set in X. So maybe I can extend them like this. All right. Wait. Okay. Okay, maybe they're coming from some open set in X. Right. Okay. Then you will retain the picture of a compact subset. Do you accept this as a proof? You accept? Okay, chop. Okay, so yeah, okay. Yeah, that's it. I think any question? Any question? So this statement tells you that these two picture actually is equivalent. Okay, if you can find finite subcover for X, right? After you take intersection, you just look at this football thing. If you start with this football, you have finite intersection. Actually, they come from open set in X actually. So you have another picture. Okay. Any question? Feel free to ask. Yes. Yeah. Definitely, because to start to do compact definition, right, you need to start with open cover. Why you can start with open cover? You can always cover it. Why? Because you have topological space, right? And then let me think. You at least has the whole space in your as your open set, right? The whole space must contain your subset, right? So you at least has X to cover it. But the problem here is you don't just consider this kind of covering. You might have other covering. Does it make sense? So one of the covering, so for example, one of the covering is A can be covered by X. This is one of the covering. But this one obviously finite, one only. But the problem here is compactness. You need to check for every open cover. Every open cover have a finite subcover. Not enough to check one open cover. You need to check for every. Is this your problem? So you want to go further? For example, A is equal. If A is equal. Mm-hmm. Uh-huh. Hmm. What can we say? That X is a subset of. No worries, huh? Here, man. This middle one is a subset of A. No problem, huh? Just that this is not enough to cover your A. You need to find some other open set and then put them together. No problem. They can stay inside A. Open set. This is a bit different from open and close, you know. Correct? Your half close or half open interval, right? It's not open or not closed, right? But if you consider it as a subspace topology, it is open and closed. This is different, no? Okay, but here, as a compact subset, as a compact topological space with subspace topology is equivalent, right? It's different from open and closed. Sorry? What's equivalent is when you view A as a compact subset, okay, it's equivalent as you view it as a compact space with subspace topology. Okay. You understand? What does it mean? What do you mean by there's no close here? We're just talking about compact. Close here means that A is a closed subset of a topological space if only if A is a closed topological space with subspace topology. This is not true. Not true, right? Last time we see that. So let me make a remark here. Similar statement. Replacing compact with open, close is not true. Okay, so consider this open, half open interval. Okay, this is not an open set, not an open subset of topology, not a closed subset of R. But if you view it as a subspace topology, it has to be open and closed. Cannot. Okay, because you can see this as A intercept with a open set. You can view this as A intercept with some open set here. Okay, or you can view it as it intersect with some closed set. Let's say 3/2 and minus 1 over 2. Okay. Any more question? No? Okay, actually, if you write down the proof, it's also quite straightforward. Okay, it's really straightforward, very short proof. But I recommend you to practice this proof here. Okay, so far so good. Any more question? Okay. Okay, so in this case, what we have seen so far, we see that compactness actually is not a hereditary property. Okay, hereditary here means you can inherit this property. So what do we mean by inherit here? So this is inherit by the subspace subset inclusion. Okay, so for example, we can see that last week we proved that the closed interval 0 to 1 is compact, right? But we can see that open interval 0 to 1 also live inside this compact set here. But 0, 1, open 0, 1 here is not compact. Okay, so what's wrong here? What's wrong? Why? What's wrong? Any more ingredient we make it in, okay, such that the subset have to be compact. Okay, what's wrong here? What's wrong here? Huh? What do you mean by 为什么意思? So why subset inclusion here doesn't inherit the property of compactness? What's wrong there? So you imagine if I have a lot of open cover for 0, 1, right? Why I cannot find a finite subcover for it? What's wrong? What's deterring you to doing that? For sure, definitely there's something to do with topology here. Okay, the problem between the difference between these two, right? There's some room to play with this open interval here. You can squeeze infinitely many open set close to this limit point. Here, because I already have the limit point, right? I just put one open ball around it. Then all the point approaching to a limit point will stay inside the ball. But here, got infinitely many point approach this one here. So because there's infinitely many points there, I can put ball around those points. Okay. Can make sense or not? Does it make sense? Let me pull the number line for you. So let us make a very long 0, 1 interval here. Zoom in, magnify this. Okay, so because 1 is the limit point, right? So there are infinitely many points, okay? Really close to this one here, okay? And then around this line, right, you can build open ball, okay? Open interval like that. Okay, not that. There's one problem here. Is there one problem here? Yeah, okay, no problem. So you can just put a lot of open set around here. Okay. So you can make your open ball actually arbitrarily small as you like. Okay, arbitrarily small as you like, actually. Okay, so the key here is if A is a closed set in a compact space, then A is compact. Okay, so the slogan here you should remember, you have to remember, sorry, close in compact is compact. Okay, closed in compact is compact. Okay, closed subset in compact set is compact. Okay, let's think about how to prove this. This proof also very easy. Okay, very easy only. So to show that it's compact, right? What's the definition? Jack. Okay, every open cover of A has a finite subcover. So you need to show for every, right? So just start from arbitrary one. So proof. Suppose that C is at open cover for A. Okay, we want to find a finite subcover again for A here. So what's the picture here? Let's draw it. So you got an X, okay, which is compact X here. Okay, and then you got an A inside here. Right. Okay, maybe you got some cover of your A. Let's draw our sunflower here. Okay. So you want a finite subcover, right? But who do you know have a finite subcover now? Who do you know have a finite subcover now? The topological space itself. Okay, X itself has a finite subcover. But do we have open cover for X yet? No, or not. Have we covered our X yet? With this open cover, can we cover our X yet? This open cover only cover A, right? For sure. Not sure cover X or not. Can cover X. Can cover X, but not sure. But are we far from covering this X or not? We just need one more open set actually. Huh? X. X is not very helpful in this case. X, A complement, right? Because we know that A is closed. The complement is open. Correct or not? Okay, so if you look at these complement, okay, so consider X minus A, which is open. Then C union with X minus A will cover X. Okay? Make sense? If you like, you can write down this detail also. Okay, but I draw it in the picture for now. You can write down the detail. Meaning you want to check. So the detail is you need to check that X equals to C union. Okay, so try and check yourself if you like. Okay, and then, so from here we can use compactness of X by compactness X, C union X minus A admit a finite subcover. Let's call it F for now. Okay, covering our X. Okay. So meaning you can pick finitely many of them to cover the whole X. But now you want to cover A. What to do here? Now you know there's a finitely many of them that can cover everything here. But you want to cover A only. So how? Hmm? Uh-huh. Uh-huh. So you're saying that A live inside because this covering X. Okay, so let me write it down. So wait, let me see. So you say that A is in X and then X equals to F and that. Then you are done. Not quite. Why? Because F contains something extra, right? Might contain something extra. Maybe F will pick up this X minus A here. But this X minus A might not live inside C. But do we need complement of X A or not to cover A? Can complement of A cover A? No, right? So the claim here is then you just take your F. If got X minus A, throw it away. If not, then it is a finite subcover of finite collection of C which cover A. Okay, does it make sense? Okay, so if you want to think using this picture, right? So you have infinitely many cover here, right? Okay, with this something extra here. But the compactness of XR help you reduce the number of this covering here to finite. Okay, yeah, either it throw the complement of A away, but definitely it reduce this covering here to finitely many. Okay, make sense? Okay, you use the compactness of X to reduce again the number of covering that you need. Okay, okay. Any question? Feel free to ask any question. Yes. Can you F intersect C? F intersect, yeah, sure. I mean, yeah, sure. Let me think. F intersect C, yeah. But this is, I think you can, yes, I think you can try and show that this is equals to intersect C. Ah, F is different from C. How is it different? Do you know? Finite subcollection of C. Finite sub. Oh, sorry. Not finite subcollection. Finite subcollection of C union the extra, the A complement. Yeah. Okay. So that's You don't know whether the complement of A is living inside C or not. Okay. So you cannot straight away like Lydia deduce that F is the finite subcollection we want because this F might contain something extra than what C has. Okay. If no, it's okay lah. But there might be the possibility that this complement of A already stay inside C. Okay, make sense? Okay. Any other question? Other question? No? Okay. Okay, good. Next. Next, we swap it around. How about closed set in a compact set? Okay, so next theorem is compact in Hausdorff is closed. Okay, can anyone rephrase this sentence here? What should I write for a sentence? If A is what? Is a compact set in a Hausdorff space, then A is closed. Good. Huh? This is my assignment, eh? Yeah, I think using similar idea here. So let's discuss this. Oh, another thing about my assignment. So there's a question about finding a fixed point, right? Finding a fixed point, fp equals to p. Again, for continuous function, mapping from interval to interval or a fixed interval. Did I fix 0, 1? Okay, 0, 1 interval. Yes, that's true that you can use the IVT, the MA solution. Okay, but I want you to use the open set solution. Okay, try and think about that fx equal to x line there. Okay, that line. What's the complement of that line? It's two open set. Okay, so you suppose that your fx, there's no x such that fx equal to x. Then your function, your continuous image of the connected set will lie on the complement of that line. Then you can create your separation. But can you separate your image or not? Cannot. Why cannot? No. Okay. Why can't you separate the image? What kind of image is that? Continuous image of a connected set. Must be connected. Okay. Yeah, try write down in your assignment. Okay, so let's discuss about this then. Right. So how to start? What's the idea here? You want to show that A is closed. So what's the definition of A is closed? Pei. Complement is open, right? Okay, so we will use that method. Okay, we want to show that x minus A is open. Okay, how to show x minus A is open? For every point in x minus A, there is a open neighborhood around this x that contains inside x minus A. Okay, you need to find an open neighborhood. Okay, so that is find open neighborhood for x such that, let's say this is u, x is u, and u is in. Okay. Let's draw some picture. Let's draw some picture here. Let's draw some picture. So let's say we got an x here. Okay. And then we got a here again. A. Okay. So we're not sure that the complement is open. Okay, the complement may be somewhere outside here. X. Okay, so meaning what? You want to find some ball, okay, outside this complement. That can avoid this because you want to stay in the. So this theorem kind of hinting you that if you want to avoid this A has to be compact. Okay. Okay, at the same time, the whole space is Hausdorff. So whole space is Hausdorff, meaning let's say if you take another point in A, right? Okay, there's some open set that can to fully separate from this compact, this set have to be. Okay. Okay. All right. So what's the strategy here? How to start? Let's start from Hausdorff. Okay, let's start from Hausdorff first. So if X is in X minus A, right? Okay, then for every other point in A, there should exist open neighborhood UA, okay, containing A. So let's call this A. And V, should we call this VA? Okay, let's call it VA. VA of X. Okay. Later you will see why we label subscript them both of them using A, such that their intersection is empty. Okay, so you could find open ball around this A here. Okay, call this UA. And then this one VA. Okay, such that these two intersections let this U. Okay. So what to do here? We use Hausdorff already, right? Next, we can use compactness. Okay, let's use compactness also. So let's say we do this method for every A in A. So we take all the UA. Okay, such that this UA is an open cover of A. Okay, so meaning let's say we call this A1. Okay, then we have UA1, VA1 here. And then maybe we got a A2 here, right? Okay, similarly, let's draw this a little bit bigger. A2 here. Maybe this A2 will touch this VA1 here so that you will see what's need to be happen. So in this case, right, we should pick a different VA2 now. Okay, so our VA2 maybe looks something like this. Okay, we can go like this. Okay, VA2 like that. Okay. VA2. Okay. So what can you see here is for each A, right, UA and VA intersection is empty, but maybe you intersect some other UA. Okay, possible. But this is an open cover for A, right? A is compact, so meaning what? So actually you can just pick finitely many of them to cover your A. Okay, subcover. Let's say our subcover is choosing from some finite set. So we name it F. Okay, so where F is a finite subset. Okay. Okay, so what can you see here? So now what we produce is, if you just consider the union of these finite open set, right? Okay, this is an open set that cover A. Okay, finite set that cover A. But correspond to this UA, right? Okay, so let's make this U more obvious a bit. Correspond to all these UA, right? There's a corresponding VA. What is VA? How do we define VA? VA are all the open neighborhood of the particular point X, such that the intersection with the UA is empty respectively. Respectively, like what I told you just now, right? Maybe maybe VA1 will intersect VA2, UA2. So how do can we avoid this intersection here? You have all the VA, okay, finite many VA that contain this V. Can you make an open neighborhood that avoid all these open set? Tiêu tiêu. Tiêu tiêu here means what? You consider E as a finite intersection of these VA. Okay, this is an open set containing X. Okay, because it's a finite intersection of open set. It's open. So now we need to argue why this is enough. Okay, to make sure that U intercept V is empty. Because if we make sure that U intercept V is empty, for sure V intercept A is empty. Because A is covered by U. You cannot meet the larger set that contain A, you surely cannot meet A. Okay, this is how we make sure that our V intercept A is empty. Okay, so how to do here? This is a set equality, right? So you just take Y in U intercept V. Is there such a point or not? Okay, so if there's a point in U intercept V means what? U is a union, V is an intersection. Okay, meaning what? Meaning Y should live inside one of the UI intercept with V. Okay. But this one is living inside one of the UI VI. Because this is the intersection. So the intersection is smaller than one of the set theory, subset inclusion. Okay. Is it possible for some I in F here? Is it possible or not? Is there anything living inside UI intercept VI or not? Jonathan. Why not? How we pick this UI VI? Okay. No, I mean like UI VI, how we choose them? From the Hausdorff property, right? So these are the two disjoint open neighborhood. Okay, so there's nothing here. Okay, so if you have something inside this intersection, you will have a contradiction. Okay, that UI intercept VI is empty. Okay, so there's nothing there. Okay. Okay, so in this picture here, right? So what you see is what we have shown is we show that there's no intersection between V and these open cover here. Okay, let's call it the whole big U here. And this is the big U. Okay, the big U maybe looks like this. Okay, and then the V, how about the V? V in this case, let's say just two of these are, then it will lie inside this intersection. Okay, can see a bit messy. So this is U, and then this is your V. Okay, so you cannot intersect U, for sure you cannot intersect A. Yes? Cannot? You can't touch the boundary also, right? Oh, wait, so what, say again? So, oh, so you mean your compact set is here. This is your compact set. And then, possible, you go back and try. You will make contradiction also. Yeah, yeah, please try it. Yeah. Okay. I think you need to appreciate these to see it. You need to appreciate this to see it. Okay, it won't happen. Okay, any other question? Any other question? Any other question? Okay. 很好，要感恩，所以要感恩。Got question? Any question on this proof here? Any question? Maybe I just say maybe your question cannot be solved in one day, but every day you ask, you answer a bit. Every day you ask, answer a bit. Then slowly, your understanding will get better. OK，不要这样贪心，不要一下子就我一定要问到然后解决完，没有可能的，那有可能有人40年、50年都没有解决。OK，呀、不懂一点知道一点，不懂一点知道一点，不懂一点知道一点，你就会知道很多。Okay, maybe we have some time to do two more things. Okay, so one more thing is there's a very nice corollary here. This particular nice corollary is if you just start with bijective continuous, okay, function. How far is this function from being a homeomorphism? Far. Its inverse is continuous. But if you know that your domain is compact and your core domain is Hausdorff, no need to check inverse already. Okay, then F is a homeomorphism. Okay, these two properties will make sure that your inverse is continuous. Very special. The property on space can tell you something on function. This one is very special one. Okay, property on space force your function to look like that. Okay, usually only function can control function, right? But now this space will control the function. Okay, very special. Okay, so this proof is also not very hard. So to show inverse is continuous, right? What should we show? Okay, so let me write down here. Is it correct or not? It suffices. Let me write down first. Let's think together. It suffices to prove that the images of closed set of X and F are closed in Y. So continuity says what? If U is open in a core domain, the pre-image is open. But now we want to show the inverse map is open, right? The inverse of the function is open. So meaning what? The open set in U is open if F inverse of U is open. Let me think. U is open. So U is open. Sorry. Okay. Go back again. So continuity of F is what? Where open? Imply where open. Image. Okay. Open set in the core domain is open first. Huh? Implies. So if U is open in Y, then F inverse X, F inverse U is open in X. Yes, good. So now we want to do the other way around, right? So if in X, imply FU is open in Y. But now we change the word open to close because this is the equivalent definition. Okay, last time we showed this TFAE, got a few continuous equivalent definition. Okay. Why close is useful here? Because previously we are dealing with close compact, right? Okay, so that's why we choose the close definition here. Okay, so if A is close in X, then what? X is a compact set of closed in compact is compact. So A is compact. But what is FA leh? Continuous image of a compact set is compact also. Last time we showed. Similar to connectedness, continuous image of connected set is connected. Okay, continuous image of compact set is also compact. So FA is a compact. But Y is Hausdorff. Compact is Hausdorff means what? Implies that FA is closed. Okay, so that's why we name this as a corollary because we are just using what we have proven. Okay, clear? You see, this proof, I didn't write F down. I didn't need to know what's the formula for F. Okay, usually 很常学生会问，哎，老师 F 要怎样写上来？要怎样写上来？不用写，不用写，我只要知道 F 是 continuous 就好了，不用写。Okay, does it make sense? Yeah. Okay, I just need to know continuity here to apply. Continuous image of a compact set is compact. Good to go. I don't need to know what's the formula of it. So this corollary actually can apply to the. You remember we showed that the closed ball is isomorphic to. So the closed ball after you identify the boundary is isomorphic to S1, right? Okay. How do we show that? We use a few homeomorphism. Okay. How to prove that they are homeomorphism? Actually, you can use this shortcut here. Okay. So instead of proving the inverse is continuous, you can show that the space you consider on the domain side is compact, and then on the codomain side is Hausdorff. Because at that time we start with a closed ball, right? Okay, closed ball is compact. Okay, and then closed ball to R2, right? R2 is Hausdorff. Okay, but from R2 to S1, you cannot quite use this anymore because R2 is not. Okay, for one of the homeomorphism, you can use this to show. Okay or not? 道生不是读到很头痛，可以用这个 proof， 因为那个太原始了，就是要一个一个说。Okay, before we go to break, last theorem which I'm not gonna to prove, I want to mention here is, if you want to check that a topological space is compact, right? In principle, you need to check for all open covering, right? But actually, you can also reduce it to a statement on covering by basis element. Okay. So this is one of the nice property if your topology is generated by basis. Okay, you just need to consider the type of covering that build up using your basis element. Okay, this is a very good exercise you can try. Okay. Any question? Can directly see this theorem or not? If you have any open covering here, because you have basis element, right? Basis element should live in every open set. Okay, then you can reduce to this open, this kind of covering. And then this kind of cover is one kind of covering of A. Okay, this is the thing you need to try and write it up. Yes. Sam is saying what? Yes. Yes, that's right. If your set is compact, yes, because covering by basis element is one of the covering. If it is compact, then that covering have to have finite subcovering. Yes. I think the harder, can you guess which one is the harder direction? Up to down. Up to down is easy, right? Because yeah, down to up is harder because you need to use the covering just by basis element to imply a general covering for any open set. Yeah, down to up is harder. Okay, up to now, you just apply one type of covering by base. Okay. Before we end, I want to make a advertisement here. So I got a friend right from Sydney. Okay, going to give a talk next week, next Monday. If you are interested, please come. In particular for the洪瑞他们没有来啊，今天考试啊，准备考试。休假是我飞去中国啊？啊，哇哦，这么爽！Rosie 没有回，没见。Okay, so yeah, so I encourage those 2309 to come to listen. If you're interested, maybe we can try to do some collaboration. Okay, maybe for FYP. Right. Who is this guy? Actually, he is my classmate before. We study in ANU before. Ever since undergrad, like you guys. Okay, sit in the class, listen to teacher, I don't understand, blur, confused, assignment very hard. Same, it's the same story actually. Okay. But we work together during PhD times. Okay, PhD time we work together under the same supervisor. So we graduate together. We are like academic brother. Okay. We graduate. Yeah. Academic brother. We are in the same tree. If you like to say tree. You learn tree, right? Combinatorics. So we have the same ancestor, academic ancestor. So after graduation, I come to XMUM and then he went to Paris, IHES, again, research institute. And then he's now moving to Sydney, just moved to Sydney, University of Sydney. And yeah, our field is quite related, you could imagine. So if you like, you could come, and then if you like, we can go dinner afterward. I will bring him to makan to eat. Okay, and then if you come to eat, maybe you can talk with him and then ask him what's the current trend in mathematics, because he's doing postdoc. So he is like working as a researcher, basically. Not much teaching. I need to ask him whether he got do teaching or not. But mostly it's research, writing paper, proving stuff. So you can ask him what's the life. Okay. Actually, I also invited him to our class actually. So probably you'll see him next week in this class. I asked him to share what's the research life is. You can ask whether boring or not. Boring or not. You see from his face, you think boring or not? 没有，他现在头发比较少。Yeah, he's not like usual scholar. You will see researcher is like, oh, the old people, right? You don't clean yourself one, the hair very long, mustache never tidy up one, right? But I think modern one is not like that anymore. I think I cannot say he make up lah, but he did how to say take care of his appearance very much actually. He got set hair one. You can see, right? Cannot see, right? God, you can ask him. He got wife. He got a wife. No, I don't know. He got a wife. Yeah. I'm not single. I'm with Max. Unavailable. No, sorry. Okay. Yeah. So try and come and listen, because you don't have much chance to come to seminar, right? I asked him to make his talk more accessible to the undergrad. So try and listen how he present. Yep. Okay. Let's break until 11:10. 有关可以。他的爸爸。对。对。Email Artin。 Yes。F，你要过来看吗？这个 F 啊，这一个 F，哪一个 F？我们好像有好几个 F。
那个
Script F 的这个 F。
啊，
OK。
我的音在里面了。
诶啊，这个那个它的 F 在哪？
这个 F 在哪里啊？这个 F 是这个 C union 这个 S 减 A，你可以想象这个东西了吗？里面的 finite subcover，你选 finitely many of them 出来吧。你能想象这个吗？你讲想象这个？这个你讲想象？
就是 C，就是很多 open set cover 这个 A，
对，所以有这样圈圈圈圈嘛。哎，好难。
然后
再加上多一个 open set。
就是外面的
对，就这大圈。
啊，
但是这几个不是有数量吗？有吗？有，你可以算吗？有几个嘛，对不对？但是我要 finite many of them， 选 finitely， 选几个？对，就这样。
为什么要选，然后就可以盖完这个 A？
对，所以 OK，你是这个题目有两个问题，一个是为什么可以选 finitely many of them， 第二个是为什么 finitely many of them 会 cover A？ 你要问哪一个问题？都要问。这样我们先解决第一个先，为什么可以选 finitely many of them？ 这个是用什么东西选出来的？我们是用 compactness of X 选出来的，知道为什么吗？compactness 的 definition 是什么？对，忘记了，你一定要记起来，不然的话你问的话没有问，不知道做么的。Compactness of X 的意思是说 every open cover of X admit a finite subcover， 就是说不管你怎么 cover 我的 X， 我只要从里面抽 finitely many of them， 它也会 cover X 的。所以现在我的 argument 是这个 union 会 cover X， 这个4个 open cover X，and then 这边就会有 finitely many of them 可以 cover 整个 X， 这个就是这个 F。
是definition 它是讲 subcover 嘛？
对，
我想象的 subcover 是它旁边的那些，
没事，
就是
没有，这个
边缘那些。
不一定啊，你中间没有的话，你怎样 cover 呢？这个的意思是这样子，如果我有一个 X，right，OK，可能我有很多个东西去 cover 它，OK，let's say 这个是 Topology，这个是 OK，有很多无限个，但是如果 X 是 compact 的话，你只要选 finitely many of them， 可能假设啦，maybe 1个、2个、3个、4个、5个、6个、7个、8个，可能8个就够了，可以吗？对，这个就是这个情况呢。这些全部加起来，我只要 finitely many of them 就可以 cover X， 因为 X 是 compact。但是现在我们还是要回来 cover A 嘛，所以去哪里找呢？其实我们差不远的，然后只要从这个 F 里面丢掉这个大的这个 open set 啊，剩下的一定要 cover A 了。其实这个要说的啦，但是应该不难吧？应该不难。你要证明的是为什么 A 会躲在这个里面，或者你可以用 contradiction。对，这个要说，其实如果你要仔细进去的话，你要说这个东西，你要说的 A 是活在 F 丢掉这个 set 里面。
我觉得莫 equality 啦，如果你丢到 X 会这样。
不一定嘛，不一定 equal 啊，因为 C 的时候都不一定 equal。你要知道这个东西是一个 union 来的哦，你要知道。open cover， 每次我们讲 open cover 的时候是在讲它是个 union 吧？我想一下，给我想一下啊，我们每次讲 open， 我们在定义 open cover 来着，我们有 union 吗？我分辨一下，feel like 没有。
然后那个事情我反而然后那个时候说是，哎，对，然后那个时候就是
哦，OK， 没有，所以OK，所以这个只是一个 collection of set 罢了。所以如果我要这样子写的话，我应该要写 union 呢，这样子。还记得这个定义吗？Union of collection of set，就是里面的 set 我跟它 union 起来。要的话也要，你要的话也这样写可以了。如果你比较，OK，这个要说，其实你要的话，这个你可以去说。可以。
因为嘞，我想出来，如果你那个 finite covering f 啊，set minus complement of a，你 set 满的时候是 element wise 再去除，
element wise 再去除，然后
就讲它做不 equality，它做不 equal，
这边都不 equal，这边
但是啊，你这个就是消掉了在 A 外面的东西，然后全部都不要。所以就算本来这个 finite cover 哦，
啊，错了，你错了。这一个我们是消掉这整个 set，
哦，你现在 set，
是消掉 set，因为这里面的东西是 open set，
你消掉一个 set，它就变成
可能这些东西还有 contain AC 的东西呢，对吗？我是消掉这个 set 变成一个 element 呀。我不是呀，
是让它消到外面这边，
哪一个？
就是
你讲哪一个？你讲哪一个？讲哪一个？你在讲这个？这一个减啊，这个减是因为刚才我把 C 里面加多一个 element 了，这个是 element 哦，你不是把来这些点看成 element 哦，它是这一个东西，就是来我把它变成其中一个 C 了，这样子，它是其中一个 open set，整个东西，对，因为这里面的都是 open set 嘛，我再加进去的应该还是 open set，我不可能加点进去，点不 open。我要把 open set 加进去，这是其中一个。等下我去掉的是这个整个 open set 给我去掉。A complement 的耐力 open set，对，因为那个 open set 不一定活在 C 里面嘛。What's this？
为了比死，
哦，Thank you，那来了，
好大吗？
啊，我回去关掉。
跟这一样。
Thank you，
明白了，谢谢。
明白，OK，好。
多拉呀，要多拉呀，手到。
问你一个问题，
什么问题？
就刚刚的那个 Theorem，
哪里？哪一个天？
再往上。啊，对，
这个。
这个里，
然后
就是它后边不是有一个那个 contradiction？
这个 contradiction。
对，就它为什么会 contradict 这个？如果 y 是 input element 的话，那也不一定 contradict。
你就问了 y 能不能活在这个 intersection 里面？但是如果 y 活在这 intersection 里面 ，y 就会活在其中一个 ui intersect vi 里面。但是 ui intersect vi 是，你看 ui 跟 vi，你看这里怎么选呢？是 disjoint 的，
对，
不可能的，它不可以活在同一个 ui 跟 vi 里面。
如果它是 input element 呢？
什么？
如果 y 是那个
empty element 也是个 element 啊，不可以有东西。现在的重点是这一个东西是个 empty set， 里面没有东西，这个等于 empty， 里面没有东西。
那 empty element，empty
element 是什么意思？什么叫 empty element？empty element 的定义是什么？我知道 empty set 吧。
empty set 里，
没有东西啊，哪里有东西？empty set 哪里有东西？有东西我们怎么会叫它 empty set？empty set 没有东西，所以我们才叫它 empty 嘛。 不可以有 non-zero 东西，I mean 不是讲 non-zero，不可以有东西存在里面，什么东西都不可以。
empty set 也不在。
你说 empty set 有没有在 empty set 里面？
empty element 不在。
什么叫 empty element？ 没有定义过这个东西，我们没有定义过，没有这个东西。
哦，
没有啊，没有什么叫 empty element 都没有的东西，怎么你叫啊？
哦，
没有东西啊。
然后还有这个，就是这句话的意义在哪里？我感觉
就是说，如果有东西在这个 intercept 里面，它就会活在这个里面，但是这里面没有东西。
对，就所以这句话它的目的是什么？我感觉
它的目的就是说没有东西在这里面，因为没有东西在这里嘛，这样 contrapositive 就没有东西在这里了。
我们前面不是已经得出来，已经
没有，这个是解释 for 是解释，为什么解释 for 是解释，
这一个就是一个 proof。
对 ，for 是解释。他是说，小心，因为他的意思是说，这个是对的，如果不对的话，这个就会产生，然就会有 contradiction， 明白吗？好 ，OK， 小心那个线，不要踩到。
没有问我。
Hello. Okay, let's start. Ăn梗，什么梗？
我看你的命。
它会动的啊。做出来了没？ OK
手上那
Okay, let's say you start with finitely many compact topological space. What's the property we can do on these spaces? One kind of construction we can do is we take the product. Okay, then this product is again compact. In fact, this is true for infinite case, but we won't prove it yet. It's called the Tikhonov theorem. Yes, so you could imagine that if we put name on the theorem, it should be hard. Okay, for infinite product, it's true also. So since this is true for all n, right? Actually, we should do induction. So let's just consider why when n is 2 is true. The case for n is 2. So if x and y are compact, so y x cross y is compact. Okay. The proof is similarly quite tedious, not hard, but tedious. Maybe let's just talk about the ideas. So what's the technicality here to show that S cross Y is compact? So obviously you need to deal with every open cover of X cross Y, right? Every open cover. But just now we have a theorem says that every open cover, if you want to check, you can just reduce to cover by basis element. Okay, so cover by basis element here, how does it look like in this space here? Still remember? Pair, yeah, pair of open set in XY. What's the topology we call it? Product topology. Okay, but this is finite, right? Both and product should be the same. Okay, no matter what you use. So that's why you have difficulty in the infinite case. We are using product. Okay, so usually when we see product, we use product topology. So yeah. So how? So let's write down first. So let's write down some idea we had. So every open cover of XY can be considered as open cover by basis elements, okay, of the form U cross V, okay, such that U open in X and then V open in Y. Okay, so now now the problem is how do you reduce it? How do you reduce the number? Again, let's draw some picture. And let's say this is XY like that. Okay, you got some point here. Okay, along this point, maybe you have an open set here, right, on this line. And then you have an open set in the other direction. Okay, so these two cross together, what do you get? Maybe you get something like correct or not? Correct or not? For every point, the horizontal direction, you have the vertical. So the problem is, you have this open cover already. How to reduce it? You cannot blindly think, right? You cannot blindly think. So what's the condition you had now? For each X direction and Y direction, do I call it XY? Yeah, okay. X direction and Y direction component, right? Each of them is compact. Okay, each direction is compact. So what should you do? You should somehow reduce from these two directions. But how to reduce this cover open covering to vertical component, horizontal XY component? How? How? Huh? And then cross. Okay, so where's my U, huh? Yeah, let me confirm. Where's my U first? So U is here, right? And then my Y is okay. So I mean for every component in U, right? And then we consider one open set for Y. And that. Okay. Yeah, good. Okay. So instead of doing that, how about do it in a vertical sense? Okay, let's do it in a vertical sense. So good. I think this is one of the idea. So let's make this point X first. Okay. And then let's consider this line here. X cross Y. Sorry? S cross V. Yeah, sure. S cross V. Sorry, here is V. Sorry. This one is V. Okay. So just now you fix one point and then look at all the open set, right? So I will do similar thing here. Let's fix X. Okay. And then look at this X cross Y line here. Okay. So on this line, right, you got X cross Y1, Y2, Y3, Y4, Y5, Y so on, right? And then these Y1, Y2, Y3, right? Obviously, there's some open set that cover them because you have a covering, right? Yeah, so maybe like this, right? Okay, whatever lah. You just take it as long as you cover this line here. Okay. But what you need to do is there's actually a homeomorphism. Okay, there's a homeomorphism from this S cross Y to Y. Okay, is it clear that what's how to say this homeomorphism? Yeah, projection. Yes. Okay, projection. Okay. So actually, this is homeomorphic to Y. So meaning what? This is a continuous image of a compact set. So in particular, this line here is compact. So if you consider all this covering here, there should be a finite subcover. Okay, make sense? Make sense? Okay. So without loss of generality, I only draw finitely many of them here. So this is the finite subcover. Okay, these are the finite subcover. What do I do next? The rest of the line, huh? Can? Sure. Okay, sure, you can do it for the rest of the line. Good. Okay, good. Very good. Okay, but okay, you can do it for that. Okay, but for each line, right? You can create a new cover now. What's the new cover here? You see, these are like not tidy up. I mean, not clean. Why is it not clean? Ugly. So you see they overlap at some point. Okay. What we can do is we can take what can we take here? Let me see how we construct this guy here. Okay, so what I want to construct here, I want to tidy up this open cover here. I want to make it a whole cover here. So do you know how to make this cover or not? Maybe later we will see why this cover is nice to use. How to make this cover? Can see the yellow one. Can see? How to make this cover? What am I doing here? Sorry? Epsilon? Epsilon? What do you mean by epsilon? What am I doing here? I'm trimming this extra stuff, right? How to trim this? These are controlled by what? The UI. Okay, let's call these UI. U1 cross V1, U2 cross V2, U3 cross V3. Okay. So what I do is, this is UX cross Y, where UX is a finite intersection of UI here. Okay. Finitely many of them because this piece is compact. Then I can find finitely many UI cross VI. And then I try to shrink the X component. Make sense? Make sense or not? Anyone know what I'm doing here?
It visually doesn't connect.
What do you mean by it visually didn't connect?
There are some places where it's not essential.
No, I just consider the X component. I just consider the X component. Let me make it more apparent here. I just consider the intersection of the X component. Can see or not? So the intersection where here, 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 here. But the vertical part, I just take Y only. Make sense? Yeah. I get it. Okay. Then, like what? Joshua say, do it for every line. Okay, do it for every line here. Okay, do it for every line. But do it for every line, what can you see here? This UX surely will cover the X component. Make sense? Okay, for example, if you take another line, okay, if you take another line here, okay, similarly, you got this UX business around here. Okay, you should imagine that this ux, right, maybe could lie very close to this point we started with. Then also have this ux here. Okay, make sense? Yes.
Interval
On what line?
so many lines on the line.
This was X line, right?
Yeah.
X line, yeah. And then, yeah. What are you trying to ask?
It's the lines highlighted in
The intersection of these yellow line. And you cannot see they are different in the x, y dimension, because we are just viewing in the x dimension only. You get what I'm saying? So for example, I'm not directly taking the intersection of these two lines, but these two lines I want to just view it in let's say for example, what color we haven't used. Okay, for example, this, right, these two, right, maybe this is like 0.2 to 0. To maybe 3, and then this line is 1 to 4, like that. So the intersection is 1 to 3. Okay, so this is just referring to the x component. Does it make sense? So here is the x component, here is the y component. Yes. Okay. The vertical part, we don't care about the vi, we just take y. Okay. Okay. So there's a tube here.
Oh, so 1, 2.
Yeah.
I flat them.
Yes, you can think like that. Yes, exactly. Yes. Okay. Because we settle for the vertical already, vi already finite. Now we need to consider different x. So we use this tube method to consider together. We use this tube method. Okay. So this tube method here, we look at all the ux. Okay, for every line we got this, do this intersection, do this intersection. Okay. And then this ux, right, will cover the whole x. Cover the whole x. But x is compact. So you just need finitely many of ux. Okay, so meaning what? You just need finitely many lines with your ui cross vi. Okay. So the horizontal component is finite. The vertical component from y is finite. Finite cross finite is finite. Okay. Yeah. Okay, so you see this is cardinality problem. So that's why we do set theory first. Yeah. Okay, good. Okay, so far, okay. Okay. So we didn't write down the word we just talk about. Okay. So let's go to next part. We'll talk about. We will return to metric space for a bit. I will return to metric space because we want to discuss about string value theorem. What's the application of compactness? Let's A be a subset of a metric space here. So to differentiate metric space and topological space, here we put xd. It's bounded, okay, if there exists a number m in R such that d of AB is less than m for all AB in A. Okay, so what does this mean? It says that if A is bounded, right, and then you compute all the possible distance between 2 points inside this A, it should be bounded by some number. Make sense or not? Does it make sense? Let's say this space is bounded. It means that the distance between both of you cannot be too large. Cannot be arbitrarily large. Is it true? At most, you only need this distance from this angle to that. You cannot be greater than this anymore. So there exists some bound, okay, for all your distance. You cannot be too far away from each other. Sorry? Because this definition here needs to measure the distance, right? So we need metric. Yeah, we need to have measurement here. Okay. So one proposition is easy to prove is a subset A, okay, of a metric space X is bounded if and only if for any X in X, there exists an N in R such that A live inside B and X. So another equivalent definition is you can find any ball, okay, start from anywhere. Then the whole set will live inside this bounded ball, the open ball here. Okay, for example, this group of people, okay, I can go from any point in this space here, X, and then I build big enough ball to include them. Okay, make sense? Make sense or not? So the picture is like this. You should imagine, let's say this is a A. Okay, the distance here, AB is less than some M here. Okay, maybe you take the furthest one. Okay, still less than M. Okay, so that means if you start from any point, okay, in any corner here, you should find a ball big enough, okay, to cover this area here. Okay. Okay, so these two have some subtlety, the differences. Because this ball here, right, it just talk about points, distance between points inside the set. But this ball concept is talking about point outside, could be talking about point outside the set. Could be inside as well. I mean, if inside, maybe it's like this. But you could see from the outsider point of view. Make sense, huh? One you view from inside, the other one you view from outside. And they are equivalent. Some more? Okay, so you should be able to view from inside and outside. Okay. Okay, very easy exercise. This one you should try. Very easy one. This one. Go and use definition. Okay, find the N. Use the triangle inequality. That's it. All right. Then, wow, this is a very nice theorem. I think you guys have seen it already in R3 with Euclidean topology. A is compact if and only if and only if it is closed and bounded. Okay, let's quickly show this. Not very hard. Okay, proof. Okay, so you already has a compact set in Rn. So to reach close, what else do you need? Do you remember last hour? Boundary. So it's close. Okay, you need to make sure that your A is, sorry, what am I talking about? Yes, you want to say that A is equals to A bar, right? A bar means what? A plus boundary, yes, correct. Okay, so just now we got a theorem, right? How to relate compactness to close. Compact in where is close? Hausdorff. Okay, so is Rn Hausdorff or not? Why Hausdorff? Use your triangle inequality. Yes. Okay, so go to Rn, find two ball. Can you find two ball or not? How to find this two ball? Huh? Before that, how to view midpoint or this might not be straight line, right? So you should join them first, right? Okay, and then yeah. Okay, from this line you should know how to build ball already. Okay, as long as you don't meet them, meet the boundary. Okay, and by theorem, A is closed. Okay, so what left to show here? We already show closed. We still need to show bounded. How to bound? There's really only one condition you can use here. You cannot run away. We haven't used. We still need to use compactness again. There's another property of compactness. Compactness of A. Wow, this one is very interesting. So if you have Rn, right? Okay, if you have Rn, let's say we draw R2. And then you have a set A here. Okay. How to show it's bounded? Just now it's enough to show it is bounded by a ball, right? Is there a natural ball you can consider here? What kind of ball? Yeah, natural ball. Huh? Rn has a natural ball. Polar coordinate. Polar coordinate. Do you remember what's polar coordinate? Your Rn is covered by a set of concentric ball. Let me think. But that one, if that yeah, sure. Yeah. Unless you want to do that kind of thing. But there's a very nice proof here. So if you consider the open cover that looks like this concentric ball. Okay, consider all of them. Okay, consider all of them. For sure you will cover one, right? For sure you will cover. Okay, for sure you'll cover because you take ON, right? But because A is compact, so this means what? This kind of ball, you just need finitely many of them to cover your A. Okay, maybe you cover up to this point. The other circle no need already. So you only need, like, for example, let's say 1, 2, 3, 4, 5. 5 of them. Or maybe just 1, 2, 3, 4 is enough already. Okay, no need this one to cover. Okay. But this means what? Like what Joshua said, you just take the largest one in this case. Okay, from here, you can pick the largest one. That is, there exists an n greater than 0 such that A is n. 怎么嘞？你的 MA 有用的啊？哦，真的咩？ Okay. Okay, so bounded. Okay, you just pick the maximum one. Okay, from this finite subcover here. Then you cover your A. Okay, because all the smaller one is living inside this largest one. Okay, so we'll say that by nested property of these open cover. Okay. Okay, make sense? Does it make sense? 原题吗？哎，怀疑是正常，你就问出来吧。问到有一天你可以把你自己的怀疑解决掉，你就是成功了，你就是老师了。你知道你跟老师差别是什么吗？你自己的 confusion 你自己解决不了，所以你需要医生，你需要什么？治疗师，你需要 counselor，因为你自己解决不了你自己的问题，你需要这种专业的人帮助。当你有一天可以解决你的问题的时候，你就变成老师了，你就变成医生了。久病成良医，对不对？你病到你会自己知道怎样解决的。Make sense？ OK， 说现在 OK， 你可以问，我能够我就帮助你，我不能你就要自己帮助你。OK， how about the other direction? Closed and bounded imply compact. Already closed, right? Okay, what else you need to show is compact? Compact in a what? That is compact. Sorry, closed in a compact set is compact. So, is it closed in some compact set or not? Is Rn compact? No. Last time we already showed that real number is not compact, right? You can use similar argument to show that Rn is not compact. But is it possible to find a compact set such that this closed set live in? You want to use the fact that closed in compact is compact, right? So is it still possible to find in between A and this Rn, there's a compact set such that this closed set live in? Is it possible or not? Is it possible? Is it possible that to find some compact set that this set can live in? Let's say this one is A. This A is closed and bounded. Closed and bounded means what? It's contained inside some ball. Okay, this ball you can place in any origin one. Okay, so maybe let's say this is the ball. This is not only a ball, this is actually an open ball. Is open ball compact? Open ball compact or not? No. Oh, do you know how to show? So you can use open cover like that just now. Okay, and then show that this open cover you cannot have finite subcover. Okay, so then does this hindering you from finding a compact set or not? Or you can use closed ball. Okay, you could use closed ball. Okay, I think another easier one is a closed square. Okay, you can choose a closed square here. Why is it easier? Let me think. I think it's the same. Okay. I mean, easier to write out. Is it easier to write out? Depends actually. Yeah. But another choice is this square here. Okay, this square should be a compact. Okay. Why square is compact? Yeah. Yeah. Why is it easier, Why just now I said easier? Just now I proved what product of compact set is compact. But now this is the product of two open interval, closed interval. But closed interval I proved that is compact. Okay, so here become easier. So if you think that closed ball is easier, then you need to show why closed ball is compact. Okay, but here we use the finite product of compact set is compact. Okay, so this is compact. Okay, so A is a compact set. So A is a closed set in a compact set. So A is compact. Okay. Okay. Okay, good. So last. Okay, I think today we are progressing well. So last thing here is the string value theorem. 来，赵胜 what's the string value theorem? Zhao Shen, what's the string value theorem here? Maximum minimum. So what do you start with? If f is a continuous function from a closed interval to R, okay, is continuous, then f has a maximum and minimum, okay, over this AB here. General Rn 啊？懒惰写它的 closed and bounded set. Okay, so let's look at this statement here. This says what? That is, there exists some point inside this domain here such that FC is the minimum and FD is the maximum. Okay. Okay, so the topology here is important. This we consider as a Euclidean topology. Both of them. Okay, if you change topology, maybe some things will go wrong. Okay, how to show? How to show? Based on what we had now. No epsilon delta, this proof. Remind you first. So closed interval is bounded, right? Okay, last time we showed it by heart. Another way to show it is this is closed and bounded. Okay, so we can use closed and bounded now. So it's compact. So image of a compact set is what? Compact. Moreover, this interval is connected, right? So it's also connected. Okay, so I'll prove here. F of this closed interval here is compact and connected. So we are using both statement continuous image of connected set is connected, continuous image of open compact set is compact. So meaning what? Meaning, how does this image looks like? What is a connected compact set? Yes, so it is some interval here. Closed interval must be closed, right? Because in R, compact if only if it is closed and bounded, and then it's connected. So meaning you cannot have something else like that. Cannot have something else because it's connected. Okay, you cannot split them. So this is actually as a closed and bounded interval. But what does this mean here? If I write like this, what does this mean? The image is equal to this set, right? This is a closed set, right? So something must achieve M and M. Okay, someone must achieve N and M. So this means that there exists CD in AB such that FC equals to M and FD equals to M. Okay, so we're done. Yeah, suggest on the image. Suggest on the image. Every function is always surjective on the image. Okay. Okay, does it make sense? Okay, you see this proof is quite short, just using compactness and connectedness. Yes. Why compact to connected? 没有听清楚啊 ，Jack。不用紧。Continuous image of a connected set is connected. So closed interval AB 是不是 connected? Okay. Continuous image of compact set is compact. So A closed interval AB 是不是 compact? We just prove that compact if and only if closed and bounded. So this set is closed and then bounded. Every distance is strictly less than B minus A, right? It's bounded. Okay. Okay. Yes. Why the M cannot be what? Oh, this one. Can M and F be equal or not? Let me think. Huh? Can it be equal? Let me think. Can it be equal? Huh? It's a constant function, right? Yeah, it can be equal actually. Yep. Can be equal. Constant function. Constant function is very good continuous function. Okay. So what you need to show is this thing is compact and connected. Okay. 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 See you tomorrow.